Welcome back to our adventures with radians. Now we're going to take the knowledge we have of radians and manipulate it a little and then do some applications. Alright, previously we were talking about radians. We discussed what a radian is. We learned that it's a pure number and it's the ratio of an intercepted arc length to the radius of a circle. If you have an angle that's in standard position and you have a circle with centered on the origin there, radian measure theta is the arc length s over the radius r. Well, we can take that formula and do a little manipulating, a little tiny bit of algebra. We can multiply both sides by r to solve for s, and we'll get s equals r times theta. But remember, this is all in radians. So we have to keep in mind that for this formula to exist and work, theta is in radians. Now we have a very handy formula for finding arc length of a circle. Arc length of an angle, excuse me, on a circle. So you can use that to find arc length intercepted on a circle. Radius r with central angle theta. Okay. And again, it must be expressed in radians, not degrees. Okay, let's say we have a situation where we have a circle. This is fun to draw. Alright, and then let's say we have this circle. And forgive me, that doesn't look quite lined up in the center, but you get the idea. And we have a radius of 25.6 centimeters, 25.60 centimeters. And then let's say we want to find the arc length intercepted by length of the arc intercepted by a central angle having a measure of 7 pi over 8 radians. So we have an angle, and we're dealing with seven pi over 8 radians. And we want to figure out what the arc length is here. So we want to find s. S is going to equal r times whatever our theta is. So in this case, finding s, the arc length, we can take the 25.6 centimeters, 60 centimeters, and multiply that by theta, which is 7 pi over 8 radians. Now remember, 7 pi over 8 can stand alone. It's a pure number. So when we multiply here, we're multiplying centimeters by some pure number, the answer is going to be in centimeters. You're going to find the arc length is going to have the same unit of measure as the radius does. Let's go ahead and work that out. Let's see. Let's go ahead and just put it in the calculator. 25.6 times 7 pi over 8. And our original problem, the 25.60 had 4 significant digits, so let's round 2 places, 70.37 centimeters. So if you took a string, let's say, okay, so you have an angle of 7 pi over 8 radians, and the radius there was 25.60 centimeters. If you took a string and laid it out from the initial side to the terminal side of the angle, But along the circle here, with that radius, the length of the string, if you stretched out the string and measured it, the length would be 70.37 centimeters. Okay. All right, let's repeat this. This time, instead of, we'll stick with the same radius, being 25.60 centimeters. But this time, let's say they tell us that theta is 54 degrees. Remember, for the formula, theta has to be in radians. So we have to convert to radians first. So if we have 54 degrees, we can times that by pi over 180 degrees. 180 degrees goes on the bottom, so that the degrees will cancel out, and we'll be left in terms of pi here. We'll have 55 pi over 180. You want to go ahead and reduce that. 9 times 6 is 54. 9 times 20 will give you 180. That'll reduce further to 3 pi over 10 if you use 2. Okay, so we can take 25.60 centimeters times 3 pi over 10 radians and see what that gives us. Alright, oops. So we'll do 25.6 times 3 pi divided by 10. And we get 4 significant digits, 24.13. And there you go. So we found the arc length of a circle. If it has that same radius, but the angle this time is 54 degrees, the length of the arc intercepted would be 24.13 centimeters. Okay. Let's use the newfound knowledge to do some applications. Let's say we have 2 cities on the Earth. Okay, let's say that this is the Earth. Here's the center of the Earth. Let's say we're dealing with Erie, Pennsylvania, which is due north of Columbia, South Carolina. So like if you were sitting on the Earth, due north, Erie, Pennsylvania is right in line with Columbia, South Carolina. Here's the center of the Earth. Okay. Now the latitude of Erie is 42 degrees north. While the latitude of Columbia is 34 degrees north. Okay, what that means is, like, if you looked at where the equator would be on the Earth, 42 degrees north is the angle from the equator that Erie, Pennsylvania is situated at. 34 degrees north is the angle from the equator for Columbia, South Carolina. Now we also know that the radius of the Earth is 6,400 kilometers. Let's figure out the north-south distance between the 2 cities. Okay, what that really equates to is looking at what is this arc length? along here. Like if you were to be, flying from Columbia, South Carolina to Erie, Pennsylvania, going straight, or if you're driving, walking, something, how far would you actually end up going? And we'll go ahead and approximate the Earth as a circle. It's technically not a perfect sphere. It's like it's squashed a little bit at the poles, and then the middle of the equator bulges, but for these purposes, it's good enough to assume it's a sphere. So what we're looking at is really a cross-section of the Earth would be a circle. And on that cross-section, here's Erie, here's Columbia, and then the center would be the center of the Earth. Equator runs along there. But we're trying to figure out what this length right here is. So we're basically trying to figure out an intercepted arc length. That's what we're really trying to compute here. And we know the formula S equals R times theta. Well, it turns out the R part's easy. They gave that to us, 6,400 kilometers. But theta we got to do a little manipulating with. Okay, they gave us the angle each one exists from the equator. Or the degrees, excuse me, each one exists from the equator. So let's subtract those to see how far apart they are. And we get 8 degrees. But then remember that this formula, theta has to be in radians. So we got to take the 8 degrees and times by pi over 180 degrees. And let's see, 4 will go in evenly. 2, 45. So we get 2 pi over 45. Not that we have to reduce that right now because we're going to multiply it together anyways, but some people like to have smaller numbers to work with. So we're multiplying by 2 pi over 45 radians. Let's see what that turns out to be. We got 6,400 kilometers times 2 pi divided by 45. And we get this. Now, original problem, you had 6,400 kilometers. Ending in the zeros, those aren't significant digits. The 6 and the 4 are. You got 2 significant digits. So we can go ahead and round this so that we have 2 significant digits, so round it to the tens place. So we get 890 kilometers. And there you go. So that's the north-south distance between the two cities. Gives you a good idea. And again, that's kind of an approximation, but because the fact that Earth's not a perfect circle, the fact that we have to worry about significant digits and so on, but still, that's how the formula works for you. Alright, let's do another one. Let's see, let's do some more application here. Area of a sector of a circle. Let's do that. Alright, let's draw a circle. Okay, and let's go ahead and draw an angle. Okay, this circle, to draw that angle in there, this little piece of pie or slice of pizza that the angle marks out for you in the circle, that is called a sector of the circle. And we're kind of curious, what is the area of that? This angle with some measure theta. And we're curious what the area of that sector of the circle is. Now for the entire circle, we know the area of a circle is found out by doing pi r squared. But we only want to do a part of the circle. I want to do a fraction of the circle. Well, if going all the way around the circle, if theta for the whole circle is 2 pi, we're technically dealing with a fraction of the circle. Whatever this theta is, it's a part of the circle, it's not the whole. So for the fraction of the circle, theta over 2 pi will give us what part we've got. So when we're doing the area of the sector, we're still going to use pi r squared because that finds the area of the whole circle, but we're only interested in a fraction of the circle, a part of it, and we can and the fraction that we're dealing with is theta over 2 pi. Whatever our theta is, assuming it's in radians, over 2 out of 2 pi total radians in the circle. You do a little manipulating here, do a little simplifying, a little bit of algebraic simplification. Reduce the pi's, and you end up with 1/2, because the over 2, the pi's reduce, and you got r squared times theta. But this gives us a nice little equation, a little formula that we can use to find the area of a sector, a fraction, or a part of the circle. Okay, let's say that you've got a sector that has a radius of 15.2 feet. Can't seem to get this pen to write today. And central angle 108 degrees. Well, this formula is for radians, so let's go ahead and convert 108 degrees to radians. So times by pi over 180. Let's see, 6 will go in evenly. Of 18 pi over 30. And then 6 goes into that. You got 3 pi over 5. Okay. So to do the area, we can do 1/2 times 15.2 feet squared times 3 pi over 5. See what that gets us. 15.2, that's 3 significant digits. We're going to keep that in mind. So 15.2 squared times 3 pi over 5, and half of that, so divide by 2. And you technically had 3 significant digits there, so you'd round to like 218. So around 218 square feet. That tells you basically what fraction of the circle you're dealing with. Now if your angle's in degrees, you're thinking about that too, is what fraction of 360 degrees you're dealing with. So either way, when you're setting up this area formula, you're doing pi r squared, but then you're timesing by whatever your angle is in radians over 2 pi. Or if your angle is in degrees, put it over 360 degrees. And that will give you what fraction of the circle. And that'll times that by the area of the whole circle, and there will be the area of the sector. Okay, so there's some application problems where we were doing all kinds of manipulating with in dealing with radians, but also dealing with arc length and radius and theta and so forth. Okay? Well, now we're going to take this newfound knowledge, and one of the next things we're going to do is develop a unit circle. This unit circle is going to be tons of fun and tons of usefulness. So please make sure you join us again very soon. Thank you for joining us here.